Well, I hope everybody is staying warm and that you've had a couple of good 2 or 3 classes so far on this e-learning day. This video is going to be a little bit of a speed walk through our target 2 notes on the transformations of rational functions. The reason we're going to go through this a little bit quickly, guys, is you're going to see we've done a lot of this stuff already all the way back in Unit 1 when we talked about transformations. We talked about this stuff in Unit 3 with quadratic functions, in Unit 4 with polynomial functions, and now we're doing it in Unit 5. And just a sneak preview, we're going to do it again with exponential and rational functions. So without further ado, let's dive in to keep this as succinct as possible, right? The first thing we've always done is we have talked about the families within the family. So the rational function family, guys, is enormous and super variable, right? There's tons of different individual families that we could look at that make up the big, broad family as a whole. We are only going to be looking at 2 specific families in that kind of tree there, and that is the inverse family and the inverse squared. And where we always start with our function families is the parents. The most basic, simplest version of that family from which all the other child functions, every other version of that family comes from, right? So these are our 2 functions, inverse and inverse squared, and they're pretty basic here. You can see the parent function for inverse is just 1 over x. Parent function for inverse squared is just 1 over x squared. You're going to see later, we're going to go into Desmos and make some tables, but those are the tables of the ordered pairs centered right around the middle of our coordinate plane using the x coordinates -2 to +2. What you should notice is, first of all, going back to target 1b, we can determine the horizontal asymptote is on the x-axis, y equals 0, because the degree of the numerator is less than the degree of the denominator. The table itself tells us where the vertical asymptote is, because when x equals 0, the graph is undefined. As we plot the other points, and if you were to graph these into Desmos, you would see curved graphs that look like this. All right, and these are pretty similar looking. They have the same asymptotes. And you can see in quadrant 1 here and here, they're actually the same curve. The big difference comes in the left side of the vertical asymptote. In the inverse, you can see the 2 curves are on opposite sides diagonally, whereas you can see here the 2 parts of our graph are both on the same side of the horizontal asymptote above it, but next to each other in terms of the vertical asymptote. That leads to our characteristics here of our parent functions. And again, you're going to see a lot of overlap here. You can see there's a lot of similarities. Asymptotes are the same, domains the same, x-intercepts, zeros, y-intercepts, end behavior, all the same. The big difference between these 2 families is going to come in the range and the increasing and decreasing intervals, right? You can see in the inverse family, it's all one and none of the other when it comes to increasing and decreasing. In the parent function, that's decreasing and no increasing. But in the inverse squared family, you're going to have one of each. Part of the function will be increasing and the other part will be decreasing. And that'll be a pattern we see going forward. In the range, you can see the range exists. The graph exists, so the range exists above and below the horizontal asymptote, where in the inverse squared family, you can see the range only exists either above or eventually we'll see below. All right, so those are the parents. And from that, we're going to get all of our children function working with our transformations, right? AH and K. Oh, sorry, guys. There we go. That's a little clearer. Right, we are still going to be using the same 3 values, A, H, and K, to control all of the transformations in these families. So the parent function values for A, H, and K are still 1, 0, and 0, right? Those are the default positions of our graphs. And these right here are the formulas that we can use to identify A, H, and K when we are observing specific child functions as part of that family. One important thing we're going to come back to later is to notice that the parent function asymptotes are y equals 0 and x equals 0. And that's going to have a connection with our values for our transformations, but we'll come back to that later. Again, this graphic right here, this table, we've had this since Unit 1. And As always, remember, guys, in an equation, H lies to you. Don't trust hippos. They want to maul you to death and fling poo all over you with their tails. No matter how cute and cuddly they seem, they're not hungry. They're evil. Don't trust them. All right, so let's chat about this first example here. And again, guys, this is the same story, different chapter. All right. So what we're going to do is we're going to compare this function to its formula to identify AH and K. And then if AH and K have changed from the parent functions, there were transformations. If the AH and K, any of those values stay the same as the parent values, then we know no transformations. So let's take a look here. So what is my value of A? Well, as we compare, A is that numerator part of the fraction there with the variable underneath. So that would be -2. H is always going to be in the denominator here, and that looks like +3, but we know that hippo is just winding its tail up to cover us in feces, so we know it's going to lie to us and actually be -3. And then K is the constant over here. K is OK, so we know K is 7, right? And I got that by looking back up here and saying, okay, we're looking at our inverse squared and identifying AH and K. One thing to notice, guys, is that in the denominator, even though x minus h doesn't have parentheses, you could put them in parentheses there. Notice that factor in front of the x minus h is 1. That'll matter a little bit later here. But we've got our 3 values, so now it's a matter of going to our list of transformations, our instruction manual, and just making sure we know what's happening. So if A is negative, well, there's a reflection over the x-axis, right? We're going to have that. And the absolute value of -2 is +2, which is greater than 1. So we're going to have a vertical stretch there, right? So we're going to have a reflection, and I'll color coordinate the values and these transformations here. Reflection over our x-axis. And, oops, sorry, switched away from red. And a vertical stretch. Oh, come on. Apparently my arrow doesn't like it when I'm recording vertical stretch by 2. All right, so as we look at our H value, remember H controls our horizontal translations. So our horizontal translations, and since translation, sorry, I can't start talking until I spell. Since it's negative horizontally is going to the left, and it is going to be 3 units. K tells us our vertical. Oops, so vert translations, and that is positive. Positive vertically is up, and up 7. We will be giving you the same word bank on a test that you've had on all of the tests. So we're not expecting you to memorize the terms, but you do have to know your playbook to know which values cause which transformations and be able to appropriately describe the direction and the values that are involved there. All right. So on this next page, you've got 6 more examples. Go ahead, pause the video, give those a shot, and then when you're ready, come back and you can see how you did. All right, ready and pause. Welcome back. So how did we do? Guys, I will be available, as I will talk about in the Zoom chat when we're doing attendance. I'll be hanging out in the Zoom chat for any questions. So as you're working through this video, if you want to wait, finish the video and come ask questions, or stop the video, pop back in the Zoom chat, ask me questions. I'll be hanging out, so please do so. All right. Most of these are pretty straightforward, except for 4, 5, and 6. There's one unique detail in 4, 5, and 6. And if you notice, that is that the factor next to the x minus h part is no longer 1. In number 4, it's 5. In number 5, it's 2. And in number 6, it's 3. And our formulas, guys, don't have a variable to account for any value being a factor being any value other than 1 in that denominator next to x minus h. So what the heck is going on with the 5, the 2, and the 3 in questions 4, 5, and 6? Well, here's the deal. The 4, 2, and the 3 are actually part of the numerator. As you can see, I rewrote the equation there, and you're probably saying, whoa, 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 how is something in the denominator actually in the numerator? All right, well, let me show you. So this goes way back to, middle school when you were dividing with fractions. And the rule when you're dividing with fractions is we're going to rewrite it as multiplication, and we're going to multiply the numerator, keep it the same, by the reciprocal of the denominator. You may have heard the phrase keep, change, flip. So you can see in this example, we're going to keep the 2/3 the same. I'm going to change the division to multiplication, and then I'm going to take the x, which is x over 1, and I'm going to flip it. And then I'm going to multiply straight across. So I get 2 times 1 is 2, 3 times x is 3x. So notice what started out as 2/3, the whole fraction in the numerator, simplifies to 2 over, and the 3, which was, listen closely, a denominator in the numerator, has now dropped down to the denominator and has become a numerator down there. All right. So conversely, we can reverse this process. So if we see a factor of 3 in the denominator, we can always move that up to the numerator and write, instead of 2 over 3x, we can write it as 2 over 3 over x. And that is exactly how we have to think of these values. And these are the situations where our a value is going to be less than 1, and we're going to have a vertical shrink. So pretty much, guys, anytime you have a factor in the denominator that is larger than the number you see in the numerator, your fraction, your a value, is going to be less than 1, and you're going to have a vertical shrink. You can still have fractions and have a stretch if the value is bigger than 1. So don't just automatically assume if it's a fraction, it's a shrink. Think about whether the fraction is greater than 1 or less than 1. Again, if you got questions, hop back in the Zoom chat and we can talk about that. But let's move on now to the second application of what we're going to expect you to do here with our two function families. And that is be able to use the values of A, H, and K and your BFFT Desmos to create a graph and then get a little more practice identifying some characteristics here. These should be pretty familiar. We've seen these before back in Target 1 there. So let's just go into Desmos and we'll model for you how to put this into Desmos and then correctly identify A, H, and K and create a graph here. So Desmos, if we come here, right, you don't actually have to type the f of x equals, but I'll just do it for appearance sakes there, 5 over x minus 2, right? So 5 divided by x minus 2, and you can see we get a graph that looks like this. All right, not bad, but not super helpful because you can see in the graph here, we need to have 2 specific points on each side of our vertical asymptote. That is going to be the requirement. Now, notice it doesn't say precise points. Precise would be non-decimal. Specific means we just need to see clearly graphed points along the curves that you're drawing there. So they're going to have to be decimals. You'll see. It's unavoidable. Right? So how, first of all, Desmos doesn't, wrong Desmos, sorry. Desmos doesn't give me the vertical asymptote. So where's the vertical asymptote? And then Desmos is not giving me points on either side of the vertical asymptote. All right, so this is where A, H, and K are going to come in and help us out quite a bit because this is where we're going to go back and talk about that relationship between these values and the asymptote. So if we write these out here, we can see A is 5, H is going to be positive 2 because it looks like negative 2, and K, right, guys, there actually is a value of K there. It's 0. All right, so you can see K doesn't change from the parent function. H does. So this graph would translate would go to the right 2 units. Well, how would that affect the asymptotes? Well, if the asymptotes of our parents, guys, in both families are right on the axes starting at 0, any transformations left or right or up and down would also cause, which are controlled by H and K, guys, would also cause the asymptotes to move to that specific value. So H is 2. We move 2 units to the right. My vertical asymptote here, guys, would move 2 units to the right and become x equals 2. If K was negative 5, the graph would move down 5 units, which would then move my horizontal asymptote down 5 from 0 to negative 5. So what I hope you see here, right, is that the H value the H value, guys, is going to give you your vertical asymptote. H is going to give us the vertical asymptote because essentially, because H starts at 0 and the asymptote starts at 0, whatever H is, that's the value of X. Conversely, oops, I'm sorry, guys. I have those colors flip-flopped. There we go. Green for H and blue for Y, right? K is going to do just the opposite. That's as we shift our graph up and down, that is going to move our asymptote, and that will give us the asymptotes Y equals K. All right, so what does that mean here? Well, that means we can identify my vertical asymptote as X equals 2 and my horizontal asymptote as Y equals 0, and we can put those right on the graph and here. So Desmos won't graph these asymptotes for you, but you don't need Desmos to if we know what H and K are, because H and K will give me the asymptotes, right? So if we come back here now to Desmos, what we can do now is we know and I'm using air quotes here, guys, middle of our graph is going to be X equals 2. So let's go to our table. And what I'm going to do is go to the middle here, and I'm going to make the middle of my graph 2, right? So I know that that's my vertical asymptote. So let's go 2 units to the left, 1 and 0, and let's go 2 units to the right. And you can see, guys, I now have 2 ordered pairs on each side of my vertical asymptote that I can graph and then use to create my curve. So let's come here, and I will grab, let's go purple. So what was that? We were at 3 and 5 and 2 and 1/4. And then I was at -1 and -5 and -2. Here's the deal, guys. Notice there is always symmetry between these two parts of the graph. If we go back to the parent function, we're expecting to see this. All right. The inverse family is always going to have symmetry kind of over the origin, meaning diagonally. So if I'm at 1, 1, I'm at -1, -1, right? If I was at 2, 3, I would be at -3, -2. The inverse squared family is always going to have symmetry over the y-axis. So if I'm at 1, 1, I'm at -1, 1. If I'm at 4, 5, I'm at -4, 5, right? So we have that symmetric relationship, and we will be expecting to see that. So once we have that, we can then just sketch curves which appropriately get closer the asymptotes, and there we go. There is a good graph of what we see here. And if we change the color too. Oh, it's not letting me change the color. Oh, purple? Okay. Done. Change the color? Yeah, let's change it to purple, just so it matches up there. All right, there we go. You can see purple graph in Desmos, pretty solid purple graph on our thing. All right, so I'm not going to bother going through the characteristics because we've done that back in Target 1, but it's really great practice for, again, a big chunk of points on your test. So there are a couple of details before I turn you loose to try these, check your answers, and come ask questions in Zoom because we'll wrap up the video here. All right. Oh, no, I'm sorry. I'll put the answers in and have you come back and wrap it up. But on 9, 10, and 11, I want you to add 3 things. Three things. 1, make each of the numerators negative. And then, guys, on 10 here, make that x minus 5 squared. All right. I realized I had a lack of variety in my examples in the notes as I was making my key. So since you're going to have to watch this and anyways, and work on it at home anyways, I'll just have you change those. So make 9, 10, and 11, make the numerators negative. And then on 10, make x minus 5 squared. All right, gang, give these a shot. Give a couple of these a shot. Check the answers. And let me start that over. Pause the video. Give these a shot. When you're ready, start the video up, check the answers, and I'll see you in the video in just a second here. Welcome back. So, how do we do? Here are the answers, right? I will eventually fill in all of these notes in Miro, but I'm intentionally not filling them in Miro because I want you to watch the video. I want you to actually engage in real time with thinking through this, watching me do some work and stuff like that so that you can, You can learn this rather than just blindly copying stuff down without really thinking about what you're writing. All right. So this is it. This is what we've got here for Miro. You can go back, rewind the video if you need to see anything. Again, later on at some point this weekend, I will fill in the notes so that you will have the completed copy of the notes here. But I will do that once once I've kind of required you to watch the video a little bit to follow along. So hop back in Zoom if you got questions. Happy to answer them. If not, have a great weekend and stay warm. See ya on Tuesday in class, hopefully in person. Bye, guys.